Okay, let's continue with another application of vectors. This is question 3 on your worksheet, application of vectors. We want to raise a crate and 2 ropes are attached to its top. Those are the black lines that I've drawn here, and I really should have drawn them with arrowheads on them. Again, we want to raise the crate and 2 ropes are attached. If the force in one of the ropes is 240 pounds at 25 degrees from the vertical, 240 pounds at, this is probably not 25 degrees, but I just try to draw my best. So at 25 degrees from the vertical, what must be the force in the second rope that's at 35 degrees? So this is my attempt to put a 35-degree angle. And I want to know what the magnitude of that force will be in order to lift the crate straight upward. So in other words, you guys, I want the magnitude of the resultant to go in a vertical direction only, and I want to raise the crate. So essentially what has to happen is the x component of this 240-pound force, which goes this way, and the x component of this force, which goes this way, they have to be equal and opposite for my resultant vector to only go upward. And what I might even do is, I think what I'm going to do is I'm going to draw our chart that we've been working with. So I'm going to create a chart whereby I have the first force, which is 240 pounds, and we'll talk about its direction in a minute. How about if, because this is 25 degrees, how about if we go ahead and call that 90 plus 25? How about if we call that angle 90 plus 25, which would be 115 degrees, in order to find its x component and its y component. And I'm just trying to set this up in that chart form that you might be familiar with after learning to work with vectors that are not applications. There is a shorter, easier way to do this problem, but I'm going to set it up like this. I think you'll be able to get a feel for this. Let's go ahead while we've done that. Let's go ahead and take 240 times the cosine of 115 degrees and get a negative number because remember, this is in the second quadrant. So the x component of that 240-pound force is this value right here. I'm going to have to grab my calculator because I know that I didn't do all of these components. But I do know that I have this one, but I'm just going to check real quick. So 240 times the cosine of 115 is a negative 101.4. What I haven't calculated is 240 times the sine of 115 degrees, and I'm going to go ahead and show that as 217.5 pounds acting upward. I think I'm just going to remind you that that's this piece of this 240-pound force. That's what that is right there. Again, to get that, I took 240 times the sine of 115 degrees to get that. In the second quadrant, which is 115 degrees, I would expect x to be negative and y to be positive. What I want is I want my resultant, here's the reason why this table might be a little bit difficult. I want my resultant to be at 90 degrees. So I want it to go vertical only. So I want my x components to add to be 0 for this thing to go in the y direction only. So what I need to have happen then is this other force that is at, so it's this one I'm speaking of right here. This is a 35-degree angle. So this angle right here would be 55 degrees, is that right? So this is 55 degrees, but what I do know is I want the x component to be 101.4 because I want these two numbers to add to be 0. So now what I have to do is I have to figure out the magnitude of this vector. So what is the magnitude of this vector if I multiply it by the cosine of 55 degrees in order for it to equal 101.4? And that's all I really have to do here. So I have to take that 101.4 and divide it by the cosine of 55 degrees to find the the magnitude of the vector, this force right here. How hard do I have to pull to make sure this thing only goes vertical? And 101 divided by the cosine of 55 is 176.8 pounds of force. So I found my answer. What's the vertical lift required? This right here has to be 176 in order for this to only go in the y direction. Now I could finish this problem if I wanted. Now that I know this is 176.8, I could come over here and multiply this by the sine of the 55 degrees, and I could find out with what kind of force, and this is what I haven't done, what kind of force I would lift in the y direction. And so it'd be the sum of these two. So the 8 and 5 is a 13, carry that 1. 8 and 4 is 12, carry the 1, 6. You'd be lifting with 362.3 pounds of force in a vertical direction because we've canceled out the x components. So kind of a tough problem. I love this problem though. I just want to lift upward. I want to lift that crate upward. Let's go ahead. Similar problem in the next page, and it's question number 5. A ship's navigator determines that the ship is moving through the water at 17.5 miles per hour with a heading of 26.3 degrees north of east. I'm going to go ahead and start drawing a picture of this. And remember, here's east and here's north. And so 26.3 degrees north of east. I'm trying to draw a 26-degree angle here. So hopefully I did a decent job. 17.5 miles per hour at 26.3 degrees north of east. But the ship is actually moving at 19.3 miles per hour in a direction of 33.7 degrees north of east because the water current is pushing it this way a little bit. I'm just going to draw several arrows. This is the way that the water is, and so it's pushing. This is what it said it's heading for. 26.3 degrees north of east at that speed, but it knew where it wanted to go, and because of the water current, it got pushed a little more northerly, if you will, and a little bit faster. So I'm going to draw this vector a little bit longer. And I'm going to try it one more time because I really want it to be a little bit dramatic in terms of longer than the 17.5. So hopefully I know what the answer is, and so I want to try to do this picture pretty well. So I'm going to try that. Come on. One more time and I'll quit. Okay, I had to give, and I had to do a little squiggly at the end here. So this is the ship actually moving at 19.3 miles per hour. That's the resultant. I'm going to put here, this is the resultant. So it's the answer to this problem. And the angle that it's north of east is 33.7 degrees. So let's set up a table for this. Again, please remember, this is my answer. So the water current is actually, if I put the tail of the water current to the head of the boat, the water current is actually, probably pushing like this. So I was a little bit, yeah, I think that's about the way it is. So the red line is what I'm trying to find. So when I drew this over here, I was mistaken. I meant that the water current was going like this. I just hadn't remembered exactly. So let's go ahead and actually I'm going to go ahead and erase all of this water thing down here, and I'm going to create a table. So, and I mean to do this in black. So I have the ship that's traveling at a magnitude of 17.5 miles per hour, and its angle is at 26.3 degrees. And then I have the water, but I don't know anything about the water right now, but I do know the result of all of this. And the result is that the ship travels at 19.3 miles per hour at an angle of 33.7 degrees. So what I'd like you to do is pause and find the x components and the y components of the two vectors that we've got here by, remember, take the magnitude of the vector times the cosine of the angle for x, and take the magnitude of the vector times the sine of the angle for y. Okay, by taking 17.5 times the cosine of 26.3 degrees, I got the x component of the ship's bearing to be 15.7 miles per hour in an easterly direction. By taking 17.5 times the sine of 26.3 degrees, I got the magnitude of the ship's bearing to be 7.8 miles per hour in a northerly direction. So that's its y component. So the 15.7 and the 7.8 make up this 17 right here that's at an angle of 26 degrees. But remember, the ship actually travels, because water is pushing it a little bit northerly and easterly. By taking the 19.3 times the cosine of 33.7, it's actually traveling in the x direction at 16.1 miles per hour, and in the y direction it's traveling at 10.7 miles per hour. Well, these are the resultant answers. What I want is, I want to get a number right here. So I'm going to kind of put a little highlighter. I want to get a number right here to represent the current, so that when I add these two together, I get the 16.1. And the same thing right here. I want to get a number right here to add to the 7.8 to get the 10.7. So 15.7 plus 0.4, which represents the x component of the water, these two add up to be 16.1. And 7.8 and 2.9, this is the y component for the water. Those two add up to be the 10.9. So these two items in pink give me the x and y components of this red line right here. So, you know, I'm going to go ahead. Here's the x component of the 0.4, and here's the y component of the 2.9. I'm going to draw a little bit bigger. Here's the 0.4, here's the 2.9, and what you need to do now is you need to use the Pythagorean theorem to find the magnitude of that resultant. So you need to find the magnitude of the resultant for the water, though. Please remember, this is for the water. So you need to take the Pythagorean theorem and take the 0.4 squared plus the 2.9 squared and take the square root of that and get that the magnitude of the water current is 2.6 miles per hour. And then the angle that that's at, you find by taking the inverse tangent of the side opposite divided by the side adjacent. That's a pretty large angle. It's 82.15 degrees. So the question was, in what direction is the water current and what is its magnitude? So it's 2.6 miles per hour at 82.15 degrees, and I'm going to put north of east, possibly. You could also calculate the little angle off of the y-axis. So you could take 90 minus the 82 and get 7.85. So you can get 7.85 degrees. That would be east of north. In all reality, you wouldn't have to put anything, because the 82 degrees is off the x-axis, and so it is just a positive 82 degrees. I'm going to come back with you and do one more problem before I leave you from Chapter 9, Section 4.